Thank you very much. Thank you for the invitation. It's definitely the most beautiful room I ever presented at. And I have presented in many rooms. This is an amazing place. Thank you for the invitation. I come to St. Petersburg from time to time, but I've never really presented in St. Petersburg. It's mostly in Moscow that I'd go to present. Which reminds me of a conversation I had with my 6-year-old. And this Russian audience will appreciate this. So I told you that I'm presenting at the seminar, and I said, "Я буду выступать at a university, right?" And she speaks good Russian and she understands Russian very well. But the problem is that she understands it literally. So she says back to me, "Are you going to sing or play the piano?" No? Okay. So I'm not going to sing or play the piano. It is about basically statistics applied to some fairly well-known conditional heteroscedasticity models, the GARCH type, right? The GAL is the generalized empirical likelihood. We'll come up with a new way of estimating models like GARCH using a trimmed version of GAL. So basically all of this long title can be replaced with generalized empirical likelihood with tail trimming. We call it GLIT, G-L-I-T-T. Feel free to interrupt. This is joint work with Jonathan Hill from University of North Carolina, Chapel Hill. And yes, I'm now at University of Sydney, having moved from Concordia University in Montreal. This is, by the way, a very big jump, because Montreal versus Sydney is about 16-hour time difference, and currently about 40-degree difference, temperature difference. Okay. So, CIREC is a research institute in Montreal that I'm still affiliated with. This is an apocalypse edition for a reason you'll hopefully understand in a second. We will be talking about heavy-tailed data, which means that the distributions of the underlying random variables will be assumed to have moments that are possibly infinite. Okay. We'll start with a moment condition, right? So everything here will be based on moment conditions. M will be a moment function. It will be data yt. Theta is the parameter we want to estimate. Right? And in GARCH models, there's this alpha, omega, beta that's usually estimated. So theta will be inside that. So alpha, beta, and omega will be the theta. Yt will be the data. Okay. So we'll start with the moments. The moments exist. So there's no problem with the first order moments. Now with standard asymptotic theory, what we need is that the variance exists for those moments, right? So the second moment exists. Now the empirical evidence in finance suggests that might be actually fairly questionable, right? So we have often moderate or extreme heavy tails in returns, right? So if we're fitting a GARCH model, it's often the case that this moment function, which comes from the GARCH model, is actually infinitely variable, right? So the variance of that moment may be infinite. It may be also asymmetric, and there's some people who looked at asymmetry in these settings. Well, what's the problem with having infinite variance? The problem is that everything breaks down, right? The central limit theorem does not apply, and as I teach in my advanced econometrics class at St. Petersburg State, we're in a big problem, right? So OLS is no longer even consistent, right? Because to have central limit theorem results, we need to have finite variance. If it's not the case, we're in big trouble. Nothing works anymore, right? So this is a way of handling that problem. Why is this apocalypse versus near apocalypse? Well, I'll say that this is an apocalypse when you can't even form an expectation. Okay, this is the case when the tails are so fat that even the first moments don't exist. Okay, and I'll say that this is near apocalypse when the first moments exist, but variance doesn't. Variance is potentially infinite. So the tails are fat, but not as fat for the first moments to not to exist, but they are fat enough for the second moment not to exist. So we'll talk about near apocalypse events. I mean, in practice, you can think about having very volatile periods on the financial markets, right? Around the crises, when things are so uncertain then that variance of the returns is too high. Here's the example of the model I'll be looking at. Let's start with what's known as the strong arch, right? This is a model of conditional heteroskedasticity where HT is that heteroskedasticity modeled using omega and alpha, so theta includes omega and alpha. It's strong because all we assume that the error term epsilon is IID from some distribution, 0 mean invariance 1. And the moment functions that result from that model estimated by least squares, for example, are this. This is the second order moment of epsilon equals to 1, and this is the product of the second order moment of epsilons standardized by 1 times yt minus 1 squared. So these are the moments I'll be looking at. They result from the arch specification and least squares type equations. If you basically take a look at this and write it out as a least squares problem. You could write it out as a maximum likelihood problem. You get some other moments, right? The point here will be not in how to construct the moment, but in what to do if the moments have infinite second order moment. Right, so I'll be talking about moments having second order moment. So this means that there is a moment function, MTI, right, whose second order, right, whose second power will have infinite expectation. Okay, so the moment function having infinite variance. What this means for this set of moment conditions, it means that epsilon that drives the arch model has infinite fourth order. So infinite conditional kurtosis of epsilons. And YT has infinite eighth order. So you would say, I mean, this is a fairly weak assumption. I mean, this doesn't even assume that epsilons have infinite second order. So epsilon might actually have finite variance, but if they have infinite kurtosis, the moments will have infinite variance and everything breaks down. Standard asymptotics does. Okay. And this is an extension to a semi-strong GARCH, which I'll skip because this is a relatively standard extension of the arch. The point is to allow for the possibility that MTI, the moment function inside the expectation, has infinite second order moment. There's semi-strong GARCH. You will actually see that many other models can be treated in this robust GL type estimation. So it doesn't have to be GARCH. There are very many nonlinear symmetric models for variance. Not even only for variance, it can be anything. As long as the moment has fat tails, the moment function's distribution is such that the variance, the integral for the variance does not have convergent tails. This is the problem we are tackling here. All right, so what to do in such cases? This is a selected sample of people's work on handling problems with infinite variable variance. But take a look at these. There's the QMLE, conditional MLE, which requires the assumption that the epsilons to the power 4 are finite. Okay, this is an assumption we'll have to relax. There is a result that gives you a non-normal limit for QMLE under heavy-tailed errors with a fairly difficult to estimate set of parameters. There are results on LAD estimator, which also assumes existing fixed finite second-order moment of epsilons. There is a weighted, symmetrically weighted LAD. This is least absolute deviation. So these are alternative estimators that are out there, but look, they either assume existing fixed moments of order 4, 2, or they use symmetric weighting or symmetric trimming. All of these assumptions are too strict. As I mentioned, there's a lot of empirical finance literature that claims that financial returns or the errors that are driving them don't have moments of order as low as 2. Okay, actually as low as 1 even. So we'll need to do something about this, and this is an attempt to do so in the setting of generalized empirical likelihood. Why is this GEL? Well, here's some reasons why. There's a fairly standard set of nice first and second order asymptotic properties of GEL. Okay. It includes a lot of estimators, including GMM, continuously updated, GMM empirical likelihood, exponential tilting, minimum discrepancy estimators are all within that family of generalized empirical likelihood estimation. There's a way to cover dependent data. It's a one-step estimator, so no problem of iterating or convergence between subsequent estimation steps. Allows for over-identification. Interestingly, also importantly, there's implied probabilities that come out of that method, so we can use them in constructing tests. And this will be an important contribution of this paper. It allows to get robust versions of tests, right? So this is robustness to fat tails of the distribution of the error terms. Okay, so any questions? The main idea will be trimming, and my co-author at Chapel Hill, Jonathan, is the one who's is a master of trimming. Actually, this is another example of we've discussed this with Maxim, that communication across universities is an important thing for promoting research. So this paper came up, the idea, when Jonathan came to visit Montreal. So take a look. The original equation is this, right? That's the moment function which contains Q elements, right? So there's potentially more than one moment condition. Like in OLS, you would have as many moment conditions as regressors, right? So there's Q regressors, you can think. T will stand for the observation, right? So this will be up to little n. So these will be observations on those stacked Q moment functions. What we'll do will be basically rank order those moment functions, equation by equation. Rank ordering means putting them in a series from the smallest to the largest, right? So from the largest negative value to the largest positive value, right? So we'll rank order them. This will be our rank ordering for each of the moment functions. And then we'll drop the k, this will be a triple index. 1 will mean that this is the smallest section of that ordering, right? 2 will mean that this is the largest section of the ordering. So we'll drop, and I will stand for equation-specific moment function, right? So we'll be trimming equation differently depending on which one that is, and then we'll denote that this is a function of the sample. Okay. So we'll be dropping this k1 I n minus 1 smallest observations, all right, and k2 I n minus 1 largest observations for each of the equations in the set. So basically we are keeping just, remember that we rank ordered those m's, right? We're keeping the middle part, we're dropping the largest and the smallest, which sort of makes sense. If you want to come up with a robust version of something, of an estimator or a statistic, what you want to do is get rid of the outliers, right? Now, but the trick here that k1in will depend on n. Right? So we'll be considering the asymptotic behavior of an estimator based on kin going to 0. So in the limit, we won't be dropping anything. So there will be no information lost in principle if sk goes to 0. So we'll actually have nothing to drop. Good. So I'll define a moment function I hat. I'm sorry, this is the indicator function I hat. That is the indicator function that is 1 if a moment function is inside the range that we are keeping, okay, and 0 otherwise. Correspondingly, the trim moment functions are now m hat star. They will be based on the initial moments trimmed using that indicator function, right? Note that that indicator function is, of course, a function of the initial moment, which is a function of the theta, right? So, we'll need to have a theta to be able to trim. Otherwise, we won't be able to trim. Good. So we now have trimmed observations. It will be different number for each equation from 1 to q, right? And there'll be n minus k1 plus k2 minus 2 observations in each of the q equations. Note that this is equivalent to keeping observations that are between the lower k1 over n and the upper k2 over n equation-specific sample fractals. Okay, so we're dropping k1 over n fraction of observations to the left and k2 over n to the right.
And, well, basically, the choice of the fractions is up to you.
Yeah, I'll tell more about the choice of the fraction in a second. Yeah. How much to trim? So more on the trim fractals. For asymptotics to be able to derive an asymptotic distribution, we need to have in the asymptotic distribution something that does not depend on n, right? And otherwise, it won't be an asymptotic distribution, right? Because n goes to infinity in asymptotics. So what is going to happen is that we'll denote by Li and Ui the support of Mi. These are the bounds in which Mi is taking values, right? And now we'll be thinking about an equation-specific population quantile. So population of mi's has a certain distribution, right? There's a distribution in the population. We get a distribution of a sample. Everything that we do is based on the sample. But the asymptotic theory that we'll need to be deriving here is based on the underlying population. Okay? So we'll be thinking about quantiles minus Lin and Uin, also functions of theta, such that the probability of observing Mi, which is below that quantile, and MIT, that is above the upper bound of the quantile, is exactly k1 over n and k2 over n. Okay, so we're equating the fractals that we're dropping with the population probabilities that Mi is outside the range of minus L and U. Okay. Good. So Li and Ui are equation-specific lower and upper tail quantiles in the population. Again, this doesn't answer your question about what K1 should be. There will be a way to come up with that, with an answer to that.
To understand it correctly, that basically that will depend on the assumption about the distribution for the underlying population, right? So when you define it.
Yes. So let's think about, again, samples and populations, right? There's a sample fraction that we're dropping, k1 over n, k2 over n. And there's a population quantile that corresponds to that fractile, right? Minus L and U. There is a sample-based indicator function I hat, right? Which is based on, on the on the interval for MIT that we constructed using K1 and K2. And there's a corresponding population indicator function that doesn't use the head. Okay, it's just the I to denote that this is different from the sample-based indicator function. Right? Good. So M hat star will be our trimmed sample-based trimming. Correspondingly, it's called stochastic trimming, right? Moment conditions. Now, the deterministic trimming is using the population-based version of I. The basic point will be that these guys will be equivalent asymptotically. How do we pick K? For us to be able to arrive at the standard Gaussian asymptotics, K needs to be what's known as the intermediate order sequence. So it will be going to infinity along with n. So, well, the K will be going to K1 and K2 over n will be going to 0 because n will be going to infinity as asymptotics requires, right? But K1 and K2 will be also going to infinity, but will allow that that growth rate to be slower than n. Okay, and that's why the ratio will go to 0. Okay. This will also correspond to the quantiles of the population distribution that we're considering for building the indicator function, going to the bounds of M, so covering the entire support of M. So trimming will be negligible asymptotically, and that's an important consideration to remember. Let's compare this with things that already exist. Other trimming schemes that are out there. There's a fixed quantile trimming, which drops a fixed fraction of outliers, fixed fraction of observations, right? So K1 and K2 over n is a fixed number lambda, or it goes to that fixed number lambda between 0 and 1. A problem with trimming a fixed number of observation as opposed to asymptotically negligible number is that the fixed quantile trimming will require some symmetry on the distribution assumption of MT. And we don't want to have that. Okay. There's an alternative of trimming by Euclidean norm, which seems to be not behaving as well in simulations. And also note here that in general, we don't need to have the same number of observations dropped on the left and on the right of that rank ordering of M. Remember? This is to allow for asymmetric distribution of MT. And if equation does not have finite, I mean, if you're an oracle and you know that some of the equations don't have a finite variance, I'm sorry, don't have infinite variance, the variance is finite, then there's no need to trim. So we may just set k equal to 1 so that there's no trimming. All right, now there'll be a very elegant representation for what happens when we trim asymptotically negligibly. That representation is based on an assumption on what causes M to be large, on what causes the fat tail event for M. Why is MT large? Well, in my moment conditions for ARCH had this format, right? There was epsilon t squared minus 1 times some sort of an instrument, WT. It was YT minus 1 squared in the first slide, right? But in general, this could be thought of as the derivative of the corresponding heteroskedasticity function HT squared, depending on what the exact model of the arch, of the GARCH, or of asymmetric GARCH, or exponential GARCH that we consider, this will be a different W. But the point is that if we look at this MT, and you can obviously say that there's two sources. Epsilon can be driving a large deviation for MT, or WT can. Right. The elegant result that I'll show you will assume that it's the epsilon that drives that result. It's the epsilon that drives the large deviations of M. Right. So trimming by parts will allow an elegant characterization of the rate and efficiency that we'll get. So this before we talk about this, this estimator will have a non-standard rate of convergence, right? We're used to having square root n type convergence. This will no longer be possible because of the trimming. The rate of convergence of that estimate, how fast it converges to the true value as n goes to infinity, will depend on the trimming, on how we put the k, right? How much we trim. Now there will be a discussion of the optimal level or optimal rate for that k, which will transform into the optimal rate of convergence for this asymptotic estimator. Okay. Now let's talk about identification. The basic identification restriction is that the moments have to hold, right? So we cannot assume that even the first moment does not exist. Right? So this is a paper about not existing second moment. Right? So apocalypse is, remember that apocalypse is when things are so uncertain that even expectations don't exist. So we can't consider that. I mean, we'll need to have at least some information captured by the moment function, moment condition right here to have the estimator. All right, so this is a no apocalypse, but near apocalypse, right? So, variability. You can think about having a crisis where people can still form expectations, but the things are so uncertain that the variance of indicators is very high, but not about the situation when everything breaks down and people are so unhappy that they can't even form expectations about future, right? So no apocalypse, but near apocalypse events, so to speak, right? The basic identification assumption that eventually trimmed equation identify theta 0. So these moment functions are identifying theta 0. Okay. Good. So there'll be a few tools that we'll be using. Recall the trimming indicator, right? This is the indicator that's based on the rank-ordered equation-specific observations for the moment function. There was this tail trimmed equation m hat star that I mentioned to you about, right? Now, serial correlation becomes a problem because when we trim, we're using information in all MITs, right? So inside here, because of this, there's this guy, right? So we've ranked ordered all m's, right? And I is a function of all m's, which makes this a function of all m's, which makes this a function of all m's, not only the tth m. The tth function, which makes that there'll be serial correlation in m hat star, even if there's none in the initial moment m and t. Okay, we've introduced serial correlation by trimming. So, and it's now well established that what you want to do if there's serial correlation, you want to use some smoothing algorithm, or some smoothing representation for the function. So you can think about this as a autoregression, serial correlation robust standard errors, right? Or heteroscedasticity and autocorrelation robust consistent standard errors that you may be familiar with from your econometrics classes. Right? So this is what it does. It just makes it smooth over all the m's that there are in the trimmed sample, so that the new bootstrap smoothed, or block smoothed, sorry, moments are taking account of the possible serial correlation between them. This is needed because we'll now be constructing things like this, things like the covariances of the moment functions, derivatives, expected derivatives of them. So here's another key tool, the deterministic trimming. remember that in finite samples, we trim using sample fractions. But those sample fractions, we know, correspond to certain population quantiles, minus L, minus U. So the deterministic trimming that I talked about will produce the deterministic tail trimmed equations. Right? Okay, so now I'm using I here because this is the, not I hat, because this is the population determined trimming equation, trimming function. So, and now all matrices for asymptotic results will be based on this deterministically trimmed equation. But because this deterministically trimmed equation is using minus L and U, which correspond exactly to the sample fractions, we will now connect the behavior of K1 and over N and K2 over N with the asymptotic behavior of the estimator, with the asymptotic limit. Good. So we'll be defining this fairly standard things that are used for asymptotic distribution of estimators, right? This is the expected outer product of the moments. This is covariance matrix, given that the expectation of the moment is 0. This is the long run covariance of the moments. This is the expected derivative for Jacobian of M star, right, where M star is now the trimmed moment functions. Vn, this will be our equivalent of the asymptotic variance. But the trick, of course, is that now it has this n here, right? The standard way would be to have this n that we would later take out in the central limit theorem representation, right? Remember, there's square root of n times theta hat minus theta. Now we'll look. There will be this n, but the behavior of this guy will determine what the rate implicit in this Vn will be. Yes?
You say that sample fraction correspond to population quantiles. Can you explain more carefully what is the mechanics of this corresponding? Is it some proportion or something like that?
Yeah, right. So let's go back here for a second, where I define them. Here. Yeah, minus L. So K1 over N and K2 over N are fractions. For example, 5/10, okay, or 5/100, okay? If you say you dropped 5 out of 100 observations. So it's a fraction. We're now looking for a probability which is equal to that fraction. So it'll be a probability of 1/100th, or corresponding to the K that we dropped, right? Good, so this is a given number. And now, because MIT has some population some distribution, okay, we're looking for the quantile of that distribution, which corresponds to this probability. Okay, so it's just quantile, population quantile. Okay. There's another key tool, self-scaling. And that's what's driving this, these results, right? Variance becomes infinite, but that scaling matrix V, when pre-multiplying, the scaling matrix V, when pre-multiplying its asymptotic equivalent, so this guy will be going to infinity if it's not trimmed, right? So the problem will be that if we trim this, we can still get the convergence of the trimmed guy to the asymptotic limit of it, and that will be called self-scaling. So we have an object that is infinite asymptotically. That object is this, right? Where S is the long run variance of the moment functions. Right? But because we've trimmed, we can now construct the self-scaled versions of these objects, right? And when we put the standard central limit result will apply. Well, this will be a robust central limit theorem, which comes from fairly recent papers by Renaud, Hill, and Hill. So you'll see in a second what I mean by this in more detail after I describe what GELIT does. And there'll be a nice example to show you how we self-scale. So the criterion of a generalized empirical likelihood, again, GELIT is generalized empirical likelihood with embedded tail trimming. You'll see in a second why it is embedded and why it is tail trimmed. You already know, because M hat here contains trimmed equations, right? They are smoothed. The block smoothing is the B stands for that, right? Good. So GAL is based on the criterion function Q and Q hat. There is the theta inside it and lambda. Theta is the set of parameters we're estimating, right? Lambdas are all those auxiliary parameters that arise in the optimization of Q. All right, so that's the criterion function. Rho gives you the form of that criterion function. If rho is such that rho of is at nu as nu squared, then we get a special case, continuously updated GMM. If rho of nu is log of 1 minus nu, then it's the empirical likelihood. Remember, this is a standard special cases of generalized empirical likelihood. Right? The first order conditions that correspond to the maximization of this criterion function are this. Right, so we're taking the derivative of this rho, so we'll end up having j in there, which is the derivative of this function, right? That's if we take a derivative of q with respect to theta. And with respect to lambdas, what we get is this is the derivative of rho, and then the inside by the chain rule, we're going to get just the m hat. Okay, and of course at the estimates, which we'll denote by theta n hat and lambda n hat, these moment conditions have to be 0. All right, so GELIT here is a solution to the usual saddle point optimization problem, but using embedded tail trimming, where by embedding I mean that we've embedded trimming inside that moment inside that optimization function problem. Computer really likes this slide. It doesn't let me go any further. Let me see. I don't know. Oh, there. Okay, there. Maybe it just takes time to see what I mean. The key assumptions on moment functions that will be used in the derivation of the main result are this. The MTA is continuous and differentiable. MT is absolutely regular or geometric beta mixing, which means that there is a possibility for MT to be dependent over T. MT is stationary, absolutely continuous, with absolutely continuous marginal distributions. And MT has a power law tails if the variance is infinite. So these are basically standard assumptions. We are not imposing much on MT by having this. We are imposing some specific family, distributional family by assumption 4. This is a family of the power law tail distributions. But the only reason why we do so is to show you an elegant representation which follows. There's no substantive reason to have that assumption. So the results of the theorem will go through, but the special case that I'll show you requires that power law distribution. The power law distributions, of course, for those who may not be that familiar with them, are such distributions that have tails, right, decaying with the power at the power law, at the power rate. So, for example, the probability that x is greater than a specific number, little x, is proportional to little x to a power, okay? And that power is minus alpha usually, right? And the trick there with the power law distributions is that for them, only moments exist of order higher than alpha, right? So what happens in what I'm going to show you in a second is that we're going to assume a certain alpha for the underlying distribution, and this will give us a nice representation for what happens to the estimator. And of course, these are conditions that correspond to the assumption on epsilons and the W, the weights or instruments in my moment functions M in the GARCH representation above. And this is also a selected list of papers that look at how assumptions on epsilon carry over onto the assumptions on M's in GARCH type models. The key result will be this, that the Vn, this is our scaling matrix that involves the Jacobian, the long run variance, right? So it's fairly, should be common, it should be familiar to you from maybe kinemetrics classes, that you would have variance that involves a Jacobian, the covariance inverted, and the Jacobian. So it's a sandwich form type matrix, right? So if you've had some hack estimators of variance, that's a hack estimator of variance. It's just that now this Vn will be pre-multiplying our estimator, giving us a different convergence rate depending on what that Vn is. And because we're trimming all these guys, right? So inside this Jacobian and the long run variance, there is the trimmed moment underlying it. The way we trim will carry over into the Vn and correspondingly into the rate at which theta n hat, our estimator, will be converging to the true value theta 0. Okay. The intuition for the proof is that the moment function based on trimming using the stochastic I, the I hat, will be approximately equal to the trimmed moment function based on the deterministic function I. And then this will allow us to expand M star around beta 0, where beta 0 will contain theta hat plus the lambdas, right? That come from the optimization, saddle point optimization for GEL. And applying self-scaled central limit theorem will get us what we need. So in a big picture, this can be viewed as a generalization of a well-established generalized empirical likelihood theory, where the generalization is that this is possibly fat-tailed data, dependent data, right? While the standard so far has been considering dependent thin-tailed data, so that the standard central limit theorem goes through. Right, so these are a few papers from the literature that handles that standard case of dependent thin-tailed data. Good. So for GARCH, what we will have, recall that previous slide where I have moments, and I told you that the moments will have infinite variance if the fourth moment of epsilons is infinite. So what we can now conclude is that using standard GEL in cases like this will not work, right? Because of the moment, not converging moment, right? Which means that the standard GEL will not be asymptotically Gaussian, right? So untrimmed or standard GEL is a problem. Will not have the asymptotically Gaussian distribution, while our trimmed version of GEL will. Okay. A nice feature of GEL is the availability of implied probabilities calculated for each observation t, right? T from 1 to little n. We can calculate pi hat. Pi hats are probabilities implied by theta hat. And right, so if you get a theta hat here, you're going to have a pi hat of theta hat here. But basically, pi hats are given by lambda hats. Once you estimated those, you can construct the pi hats, which are called probability profiles. Right? And these are empirical probabilities profiles or implied probability profiles. So we can now consider estimating the things we needed for this scaling matrix, right, Vn, by using this implied probabilities pi's, right? We can estimate, for example, the long-run covariance matrix, so the expectation of this, using the implied probabilities as weights. You can do the same for the conditional derivative, right? Which is nice because of that self-scaling tool, giving us the possibility of using such things in the construction of the estimator and its evaluation of its asymptotic distribution. Sorry, that's not it. Not yet. Yes, not yet. So this is the example that I wanted to show you because it gives you an elegant representation of the rate and what you might call efficiency. Or efficiency is a sloppy term here because really there's a different rates. So take a look at this. I mean, the intuition for trimming and for omitting outliers is that we lose observation when we drop observations from a sample, right? That means we lose information. Right? Every observation is information. We drop information. That means that our estimator, which is now based on smaller information, right, will not be as precise as the one that used a lot of initial information, right? So when we talk about efficiency, we talk about information. Right? An efficient estimator uses most information, right? And consequently, it's the most precise estimator. Now, if we drop information by omitting observations like this, we're going to lose information. So the estimator will not be as precise. But because we drop observations in the tails of the distribution, we concentrate mass around the center of that distribution, right? And the more we drop, the faster we get to the center, right? Which tells me that the convergence of the resulting estimator is larger, is faster, right? So, and this is the intuition you should keep in mind. By losing information, by dropping, omitting outliers, you get faster convergence, but the efficiency, the variance equivalent of that information will not be as good. So let's take a look. QMLE type equations, exact identification, symmetric trimming for simplicity. The moment function is epsilon t squared minus 1 times w. M star is the truncated moment, and I am using a fixed number to truncate c, right, to truncate the moment. So if the moment function is greater in modulus than c, then I'm dropping that observation for the moment function. WTs are uniformly bounded for now, so the only, remember that trimming by parts, the only source of trimming here is the large errors epsilons. Xi t will be epsilon t squared minus 1, so if that's large, xi t is large. The moment function is now it can now be rewritten as xi star t times w's are not trimmed, just the xi's are, right? And that's how we trim them, by using a rule that if epsilon is greater in absolute value, this is our m, right? So this is the same rule. If epsilon is greater in absolute value than c, we'll drop that epsilons. Okay, good. So the results that come from our definition for Sn, Jn, and Vn are this: that the long-run covariance will be a function of xi t star squared, right? It's the expected value of the trimmed moment function squared. Then there'll be expected value wt prime. Right, so there's no problem with this. This is fine. It's this that goes to infinity. And that's why we trimmed it, right? All right, Jn will be also fine. There's no problem with this. Wt's are all good. Well-defined conditional, well-defined expectation. Now the Vn that results will have this interesting form, right? So this is the part that comes from w's. That's the part that comes from xi's. And that it's because this goes to infinity, we have a problem and non-Gaussian asymptotics. Take a look. This tells you that the order of Vn is at max n, right? And so, but depending on how we trim, this will have a different order of convergence to its population equivalent. And so, if we trim more, this will affect, in a certain way I'll show you, this order. It will be less than n, but the exact way it is affected will be here. Okay, so this is just rewritten Vn. That's our scaling matrix, which is the equivalent of the variance matrix in the standard case. Good. Note 1. The rate at which Vn goes to infinity is controlled by the error fractile. So it's controlled by the way k epsilon n goes to infinity. Right. So this is the k that's used for trimming. Right. So this c epsilon n gives us that quantile that we used, right? The L and U that we picked to define the population-based trimming indicator function I. But we can write it out as a population. So this is the population quantity, right? And that's the sample equivalent that's used to define that population quantity, define the C. So k epsilon over n is the fractile used to trim. Good. And so basically the behavior of how k goes to infinity will drive the way Vn, the order of convergence of Vn. If epsilons, the second order of the epsilons is less than infinity, then there's no problem, because this will have a well-defined limit, and this n will be standard, right? So the order of Vn will be proportional to n, and we're in classical standard Gaussian asymptotics. If the epsilons, however, are such that the fourth order moment is infinite, then the order will be less than n, because we will be defining by something that goes that has a certain rate, which will depend on the trimming. So if we assume the power law tails, then we can tell exactly what that rate will be. So let's assume that the power law tails apply to the epsilons, which means that the epsilon will be larger than some number epsilon, with the probability proportional to the power k. Right. I'll assume that k is between 2 and 4, so that remember I told you that if epsilon is distributed according to the power law tails, then it will not have existing moments for that are greater than k, the exponent of that power law distribution. So if k is between 2 and 4, epsilon will not have fourth order moment. Okay. All right, good. So what does this mean? This means that this probability, okay, is proportional to epsilon to the power minus k, right? But epsilon, that fixed number here, is c. Okay, so that means that k epsilon over n, that fraction that we drop, is proportional to c to the power minus k. Okay. So c becomes proportional to n over k to the power 1 over, I should call this kappa to distinguish between kappa and k. So this is kappa, the tail exponent for the power law tails. Okay, good. Then we can use this the Karamata theorem, which allows us to derive expectation of a trimmed moment. Right, so this is my trimmed moment in terms of the probability distribution of the underlying epsilons. Okay. Turns out that moment will be proportional to c to the power 4 probability that epsilon in absolute value greater than c. Good. Good. So now we can use that expression here. Okay. That'll get us here. Turns out that Vn, I meaning that it's it is the diagonals of this matrix Vn. The diagonals of this matrix will be proportional to n. Then there'll be this. Well, this guy is fixed. There's no problem with that. But this is a function of n, right, and a function of k. There's also a function of tail exponent kappa. So that shows you that the rate of our estimator's convergence is a function of how much we trim and how fat-tailed the underlying distribution is. Of course, we don't observe how fat-tailed it is unless we estimate that somehow in the first step estimation. But this is there just to illustrate what happens to the estimator when we trim. So here's what happens. There is sort of an efficiency and convergence rate effects. So Vn is proportional, right, to n. There's k over n, kappa, and the expected value of the weight weights outer product. Good. So the effects are from the weights, but that's fixed. There's nothing we can do about those. The trimming policy, k epsilon, that we can choose, and the tail thickness that underlies the model. Good. So let's take a look at a specific rule for trimming, k epsilon, proportional to lambda times n over log of n. So this is a trimming which goes to infinity, but at a rate lower than n, right? And lambda determines how close k is to n over L of n, right? How close it is to that lower rate of convergence. Then we can write, sort of sloppily write things that depend on n together and call it the rate. So here we go. We now end up having an estimator that has a convergence rate which is smaller than square root n, right? So this is one half of this that we're, well, actually one half of this Vn that we're using, right? And the rate, so how much slower than n the estimator is, depends on the tail exponent of the distribution. So, of course, right, so there's the lambda that we use to construct the trimming policy. The conclusions here is that the less trimming you use, so that lambda goes to 0, the higher the efficiency we get, but the slower rate, because the rate becomes slower. And that should make sense. So we don't drop many observations, right? Which means that the distribution is still, there's no redistribution of mass towards the center, right? Which means that the rate is slower. The fastest rate attainable is at lambda equals 1, and that gets you the optimal or fastest optimal trimming, which corresponds to the fastest rate available for this trimming policy, n over log of n. Okay, and the thicker tails with kappa going to 2, right? So meaning that lower order moments not existing will also produce lower rates of convergence. Should also make sense to you, because the more outliers there are, the more you'd have to trim. Okay? Yeah.
I'm sorry for maybe simple questions, but do you understand well that you always use symmetric trimming, so the center of the center is in there always?
In this example, yes, but not in general. No, K1 can be different from K2.
So it depends on the thickness of
different tails, so the two tails, right? So you may have different exponent for one tail than for the other, right? So the results provide for the possibility of having non-symmetric distributions, so different tail exponents. But this example is for a symmetric distribution. All right. Now, if you, I was still very vague about how to pick the right trimming policy, right? So lambda, I told you what to do, how to get the optimal lambda in a specific example case where I know what kappa is. Usually you don't, right? And you don't even know what the distribution family is from which the epsilons are coming. So there's an optimal fractal selection, a general approach that has been developed. I'm not even sure it's in the current version anymore, because it has sort of branched out in a different paper. But you should just take my word that there are methods existing for data-driven choice of lambda and correspondingly k. One such way is the so-called pseudo-minimum covariance determinant, which it sort of works like a scree plot. Do you know what a scree plot is? If you've had the factor analysis, which I think is a very popular type of unsupervised learning algorithms especially in this part of the world, there's something that the factor analysis is about picking the number of factors for a covariance matrix, right? And you'd be looking for largest eigenvalues, and the corresponding eigenvector would get you the linear combination that takes out most of the variance in the set of covariance. And then so you add principal components until you observe that there is no change in the variance that an additional component gives you. And that's called a scree plot. You can draw the change in the variance as you add components, as you add the eigenvalues to the principal component analysis. This is sort of similar. You can we'll look at the determinant of the variance, our equivalent of long-term variance of the moments as hat. Right? And we'll look for lambdas in a set, capital lambda, that you have to define. It can be between 0 and 1 if that's what you need for the trimming policy G that you chose. And so you'll be looking at the lambda which minimizes the ratio of that determinant to the maximum determinant available if you were to look through all the lambdas available in the set. So sort of a similar logic to the number of principal components, because you keep looking for lambdas, until this. In principle, the optimal lambda should be somewhere where that determinant is close to the maximum, right? So this number is equal to 1, but you can stop somewhere far, not exactly at 1. Good. So there are alternatives for picking the lambda star, but I don't want to talk about them. Finally, but not less importantly, GEL is very useful because of the battery of testing procedures that come out of it. These tests have been studied for the untrimmed version, right? And here is a couple of papers, including Kitamura, that looked at this results. So we can now, based on this Gaussian asymptotics for the trimmed GEL, come up with equivalents of such results, right, which will now be robust. So that's the same setting in which you make test statistics done after no less regression. You make them robust to things, right? You can make it robust to heteroscedasticity, and I'm making it robust to violation of the second order existence, violation of violation of the existing variance assumption. Okay. So how do we do this? Fairly standard once you got the thetas and the lambdas from the GEL estimator. So I may not even spend too much time on this. This is just the generalized version of the likelihood ratio test, the score test, Lagrange multiplier test. Score is also known as the Wall test. So these will all be standard asymptotically distributed as chi-squared with q minus p degrees of freedom, where q is q minus p is the dimensions of the theta. Where the theta, all right, so this is the over-identifying, so this is the number of, so this is W2T, right? So it's the over-identifying restrictions of the GEL model. So it's fairly standard. If you know GEL, you see how this, immediately see how our estimator gets you a robust version of the tests that GEL provides. By the way, you can use any consistent plug-in estimator of theta to robustify the GEL using our procedure. There's also a very neat result on the estimation of moments, and I probably won't talk about this. Just mention that there is the paper considers estimating expected shortfall. Right, expected shortfall is a very important financial tool, risk management tool, right? And this is a conditional moment that you can estimate under the assumption that the moment function does not have a finite variance by applying this robust methodology. And this gets me to some slides are more interesting than others. Okay, I'll skip this. This is I'll just get to this simple simulation. There are more simulation results in the paper, but this is illustrative and nice to conclude with because it will give you a snapshot of what this paper does. All right, so GARCH 1.1. I'm sure you look at GARCH 1.1 in financial econometrics classes or in econometrics classes. What do you do with GARCH 1.1? You go to a software and you have the time series of returns. You specify number of legs for y, number of legs for sigma. It's GARCH 1.1. So you just run and it will get you an output. It would usually be an MLE-based output, conditional MLE, assuming normality of the errors. Well, that assumption is a very strong assumption, right? Because what most software packages would do for you by default would be assume that the variance of epsilons is finite. Right? And that's a very strong assumption. But that assumption is needed to provide nice Gaussian asymptotics, right? The ability to test things, to predict things, to build confidence intervals, and all of that. All of the things we'll know and love about econometrics, right? Well, the point is that these are all invalid things. All of this stuff is invalid if the underlying distribution is fat-tailed. So let's take a look at such case. Epsilon will be assumed to be IID Pareto with kappa 2.5, which means that actually as low as the third moment of epsilon does not exist. Which will carry over into not existing second order of M. Variance of M does not exist. Good. I mean, we can still calculate QMLE, right? This is what your software will give you. By the way, I'm only estimating beta 0. So I'm only estimating this guy. I'm not estimating this parameters just for simplicity, right? I mean, this is my data generating process. I'll be generating 10,000 estimates of the known parameter of 0.6, right? And I'm going to consider the bias, right? So the average distance between the true value and the estimator, and the root mean squared error. So the measure of variability, well, actually, of bias and variability of that estimator around the true value. So you can still run QMLE, right? So you can still run the standard software packages that you know, the ones you fancy. All of them will do this for you, but the problem will be that the test statistics, the estimates, the standard errors, confidence intervals will all be invalid. Okay. They will be invalid because asymptotics fails, right? So this is a problem even asymptotically. It will not fix the non-existent moments. Central limit theorem will not do this, right? And you can see this in that simulation table. If you look at KS. KS is the Kolmogorov-Smirnov normality test divided by the critical value, 5% critical value of that test. So this number can be viewed as the distance from normality. The QMLE, the standard thing that the software will give you, is fairly far from normal. The GEL, which is that same method, but not using the trimming, will also be fairly far from normality. The GEL, it will be fairly close to normality, and that's because we force it to be normal by trimming. So now, when you get the results from our estimator, that set of standard errors, confidence intervals, all of the nice things from there will be Gaussian, will be standard normal. So you can actually comfortably test things about GARCH now. Okay, you couldn't do this before because the asymptotic distribution just was not normal. Now it is, well, basically this number is one indication that it is. Also take a look at the bias and root mean squared error, which suggests that yes. So if you run QMLE, pretending that everything is normal, variance is finite, you're going to get some estimate, right? That estimate will be slightly biased, more biased than these two alternatives. But the root mean squared error is actually better than anything else. But it's just that the inference is a problem. Inference meaning testing, confidence intervals, all of that is not correct. GEL untrimmed is also acceptable based on these numbers, but it's just not Gaussian. While GEL, it gives you a very nice bias, and I mean, very small bias, right? So we get a nice estimate, which is in fairly small samples, 100, performs very well. That we achieve by doing something that I didn't mention, which is recentering of epsilons. But this is a trick which is allowed in our settings because we can manipulate M's. But I think it's still a fair comparison of recentered GELIT with the standard GELIT and QMLE. So the most important part is, of course, that we're now in Gaussian asymptotics, and this is the table that shows you that we are. Okay?
Do you have a number on like on average, how much of the data was trimmed?
Yeah, not for this. I mean, I have very many simulations, and this number will be different for each one. I don't remember what it is for this one, but it's usually. I mean, this is 100 observations, right? So it will be 1 or 2, maybe up to 5, but this will be a small number. Yeah, and that number will be different for every Yeah, moment function.
Did you consider a case where these outliers are coming up in the data like subsequent periods, like a period of like extreme negative returns, like market crash, but they're subsequent. It's changing the behavior of the data. And if the trimming is too strong, you will be basically cutting off that part of data.
Yeah.
Like this trimming is. Question.
But look, so GARCH will take care of that clustering by itself, right? And now the question is, do you want to trim within that cluster? Of course, I mean, if it's a high volatility cluster, this procedure will pick those abbreviations in that cluster and trim them, right? I mean, this when you do this anyway. So when you
I'm not sure right now, but I think there are some models or estimations that are like robust to outliers. That include to the model or estimation. And for example, if there is such a data where there are these negative subsequent returns, extreme returns, you will be trimming while they will be including. So is there a simulation that will be comparing it? Like
including what?
Small sample size.
So
I don't remember right now the reference of the.
Well, if you when you do, let me know. No, there's a number of things with robust estimation and outlier robust estimation.
I think it would be interesting to compare with this small sample size.
If you have a specific methodology in mind, that I'll be very happy to see. I'll be very happy to look at it and see if we can compare them. But there is no asymptotically negligible trimming. All right. So most of the things I mentioned to you before, right? There are results that they either assume existent moments of fairly low order, or trim based either on fixed quantiles, so not asymptotically negligible, right? And usually the results of such estimation procedures are messy, meaning that we don't get the Gaussian asymptotics. It'll be usually something else. Sometimes people weight so some observations get deflated when they are large, right? But so those weights carry over into the asymptotic distribution of that estimator, right? So there's all this problem of how to get those weights. But anyways, if you have an idea for a specific alternative that would be interesting to see, I'd be happy to see it. All right, then concluding remarks, and we're just on time. So GL is generalized enough, right? It's generalized empirical likelihood, and we are generalizing the generalized. It's a generalization of GL with tail trimming, theory for nonlinear GARCH, or linear GARCH. Note that indeed M, that moment function, can be anything, including least squares, right? There's the moment function that corresponds to least squares, can be used here too. So there's dependent fat tail data with asymmetric distributions that we consider in cases where there is near apocalypse, meaning that the distribution is such the tails are moderately fat, meaning that the variance may not exist but the expectation does. Worked out optimal convergence for some cases, for example the QMLE equations with bounded weights and symmetric errors. Considered tail trimming by various parts. There's robust estimation procedure that comes out of this paper. There's a robust moment estimation procedure. One of the important question is whether GL has this nice set of high order optimality. Right, so the asymptotics of high order could be looked at, and we wonder if the trimmed version of GL will inherit that from the standard generalized empirical likelihood. And this brings me to the end. Thank you very much. Thank you.